Great. So I can then move on to Will Brownlie from the UK Centre for Ecology and Hydrology, who will talk about the integrated sustainable nitrogen management and nature-based solutions. Will, the floor is yours.
There you go. Can you hear me?
Yeah, we can hear you well.
Great. Hello, everyone. And you can see the screen okay?
Yeah,
Yep.
that's clear.
Brilliant. Okay, so I'm going to say something I'm not sure if I agree with yet, but I'm going to say I would say any measure to deal with nitrogen loss is a nature-based solution. And I'm going to sort of argue that case throughout the next sort of presentation on integrated sustainable nitrogen management and nature-based solutions. It was good to see Tom's talk. He covered quite a lot of things that I thought I was thinking of covering and just thought, I suspect somebody else is going to talk about lake restoration because this is a group of lake restoration experts. So I've tended to be a little bit more high level and a little bit more philosophical about how to integrate nitrogen management, but also you can change nitrogen to phosphorus or a different nutrient, but we'll get through. So I kind of thought, and I checked with Brian earlier, whether people on the call would maybe be up to date with nitrogen and nitrogen pollution. I work on phosphorus and nitrogen, but when I started working with nitrogen, I had to remind myself of how nitrogen works in the atmosphere, how it works in our anthropogenic cycles. So I'm going to run through that very quickly. Many of you will probably know it, but we'll work through it. So N2 is a triple bonded gas. It's 78% of the atmosphere. To break that incredibly strong bond into a reactive state, into a bond that is bioavailable, naturally takes something like lightning or a volcano, huge, great big power, such a strong bond. But if you can do it, then it becomes bioavailable, and you end up with these reactive nitrogen molecules, compounds, which I'm going to talk a lot more about today, but I'm just going to say reactive nitrogen. That includes your nitrate, your ammonia, your nitrogen oxides, your nitrous oxides. Now, up to a certain point, that was a natural system. And then around 1918, you had Fritz Haber, who was a very polemic kind of character, combined with Carl Bosch, and you ended up with your Haber-Bosch process. If you look into that story, it's fascinating, but we don't have time today. But through their Nobel Prize-winning science, they worked out a process using catalysts where we could replicate that breaking of the triple bond to make a bioavailable form of nitrogen, and that's where we got the modern growth of fertilizer. And of course, that use of Haber-Bosch to make synthetic fertilizer pushed forward our mining of phosphorus from our guano reserves to keep up with the amount of nitrogen we were producing. And the background of that is, as soon as you did that, see the star down there is where synthetic fertilizer Haber-Bosch happened. If you look on the left, that's world population. If you look on the right, that's a list of different things: world population, percentage, fertilizer inputs, meat production. The important thing to look at here is where you see that star, you can see that the population suddenly started to skyrocket. That also fits with meat production. And if you have a look at the very right side of the scale where we are 2024 now, you can see without that one reaction, we would have half the population we have. So half the people on this call wouldn't be here. Half your family wouldn't be here. Haber-Bosch, that reaction has changed the way the world works and also how much pollution we produce, not just nitrogen and everything else. So when we look at the creation of reactive nitrogen, which we just mentioned, around half of that is natural fixation. Of course, I didn't mention clovers, nitrogen fixing plants, microorganisms that can do that, breaking of the triple bond. But also you have fuel combustion, biomass burning, but importantly, fertilizer there. And you can see that 50% of total nitrogen fixation, that's turning N2 into a reactive form, is human led. And that creates problems where we have points where parts of the planet here. The dark areas are where we're putting too much nitrogen, bioavailable nitrogen, reactive nitrogen fertilizer onto our crops to grow our crops. This is more nitrogen than we need, and that results in losses. So when you look at your losses, the kind of nitrogen losses we are getting, and the ones interested on this call, I guess, are the hydrologic nitrogens, the nitrates. You also have ammonia and NOx. And my original statement that all nitrogen measures are to do with nitrogen, all nitrogen measures are to do with NBSs. We'll look at that and why in the next slide. So any loss of nitrogen, because it's a cascade molecule, that's in the next slide, can have any of these threats, or in fact, in the lifetime of a reactive nitrogen molecule, it will create these problems. Wages, we call them wages of too much nitrogen. That's issues of water quality, air quality, greenhouse balance, problems to ecosystems, and problems to soil quality. So what I'm trying to get to is this. This is the simplified view of the nitrogen cascade. So on the left, you see your inputs of nitrogen. If you just follow the blue arrows there, you see what we're trying to do, right? We're trying to take fertilizer, put it onto crops, it goes into your livestock farming, and then that livestock manure goes back into your crops, and you have a nice circular system. The reality of it is, though, that nitrogen losses go through, reactive nitrogen molecules go through a cascade. So it's a situation where any one nitrogen reactive molecule transitions through all of the different forms. So you release one nitrogen reactive form, and it can cause havoc all the way through its life till it eventually denitrifies to nitrogen gas at the very end of that. So that means you have ozone problems, you have urban air quality, you have stratospheric ozone loss, you have greenhouse gas balance problems, and then you have terrestrial eutrophication and also natural ecosystem eutrophication through eutrophication of lakes and coastal waters. So surely we just need to talk to farmers. Well, this is very difficult. Food security is an important national priority for maybe most or all countries. Non-point source pollution, very hard to monitor and enforce policy on. And agricultural lobby, and farmers especially, they're a huge, powerful political force globally and nationally. I mean, if you look at India, you can't put any policy through governments without having an agricultural lobby, because they're so powerful in the government. But actually, the reality of this is it's not just farmers, it's also society. If you look now, there's the addition of societal requirements. That's actually the engine driving this whole nitrogen cascade. And then when you actually look at what's driving food systems through there, you can see there's farmers right there. Right to the left, you can see aquatic resources. But if you have a look around, there's huge amounts of impacts and stakeholders driving these food systems, which are creating all the pollution we're talking about. So what are we doing about it? Well, there's a project here I'm telling you about, which we're running at the UK-CEH, which is called the International Nitrogen Management System. It's been running for a while now. It started in 2017. It's funded through the Global Environment Facility, 80 project partners. It's a joint activity with UNEP and UK-CEH and ourselves. It's a science support system for international nitrogen policy development, part of the UNEA Resolutions that were mentioned at the beginning of this meeting. The INMS has been influential, highly influential in driving those. And what one of the main calls for through this project is that we need an integrated approach to this nutrient challenge. The nitrogen is the focus, but certainly the INMS has funded work on phosphorus as well. And they're very aware that this is a holistic approach we need to do across the whole nutrient cycles. So this transition to a circular system, this is in parallel to the cascade you saw where there was havoc everywhere. This is a nice, neat diagram. I'm not going to go into detail with this, but you get the idea that you put nitrogen fertilizer in on the right. You hopefully end at a point where you can maybe remove that, and it goes round and round and round, and it's a self-feeding snake where everyone's happy and pollution is minimized. So the INMS Nitrogen Measure Database, which is the work that I work on, among other things, is an online resource where we're looking at 140 measures across the whole anthropogenic nitrogen cycle. And I would say all these measures are NBSs. And the idea of the database is it's a searchable online portal that provides huge amounts of information to a range of different stakeholders to support implementation of measures to fix nitrogen losses. So the measures, we broke the measures into different stages of the cycle. Across here, you have fuel combustion systems. Within these boxes, I'm not going to read them all out. There's plenty online about this, and I'm sure the presentation will be shared afterwards. But it's difficult trying to work out how many measures you're going to extrapolate to and how to combine them. So we've tried to provide the minimal amount of measures possible that doesn't oversimplify. And underneath each of these stages, not necessarily sector stages of the nitrogen cycle, we have groupings of measures. So the ones that would be particularly pertinent to this call that Tom talked about would be down at the bottom here, aquatic resources. So optimizing nitrogen inputs to aquaculture systems. But of course, that relies on measures within all the other stages, specifically livestock systems, I guess, and cropping systems. Biofiltration of aquaculture discharge waters. That's, turning those nutrients into something useful, into, a food product, a sea cucumber, whatever you want to do with that. Aquaculture with recovery of nitrogen into living biomass. That's your turning your pollution into food for, I don't know, shellfish. Aquaculture sludge management. Can you take that aquaculture sludge and put it back on your fields to grow your crops? And then water body management measures, which were, things like buffer strips. Okay, so the measures by group, that's what I sort of went through here. We have crop farming measures. The numbers behind that is the behind each group is the number of measures that we've included in the database, which is online. You can go and look at it, or it will be online in the next couple of months. You can go and look at it. So we have livestock farming measures. We have land use and landscape measures. That's including drainage and erosion control, landscape planning measures. We have aquatic resource measures, which I just went over. Organic residue, so that's wastewaters. That's how to take your nitrogen, I guess, and your phosphorus out of wastewaters. And then optimizing societal demand. So do we transition to healthy, low meat diets? Would that help? And then you have fuel combustion, which is really more to do with nitrogen than phosphorus, or not at all to do with phosphorus, really. And that's looking at how you can reduce NOx generation in fossil fuel combustion. So the principles of integration, which is really the sort of, within the title is, this can be, I'd say nitrogen management here, but I think this applies to phosphorus management largely, is that, the first principle, there's 22 principles. I've reduced this down to 9 for the talk, is that integrated management should consider all nitrogen forms. So when you're looking at that cascade, you need to think about all the nitrogen. You don't want to just focus on ammonia losses, for example. And you need to look across spatial and temporal scales. So different times of year, different kind of nitrogen forms might be produced. The same with phosphorus. For example, is summer a more important time to look at that phosphorus release from sediments within your lake water body? Control of nitrogen input can influence nitrogen loss pathways. So this is really combined very closely with the next principle, which is any reduction in nitrogen loss must be matched by a decrease in nitrogen input and or decreased outputs. I'm going to chuck onto this figure because this explains this really. If you look at the nitrogen system as a pipe system where you put a nitrogen input one end and you get a nitrogen output the other end, and you say there's lots of leaks all the way through the different stages. If you put your management in place to close one of those holes, just by mass balance, you're either going to get more pollution at somewhere else, or you're going to get a bigger output. So therefore, if you're going to manage your nutrient system here, you either want to reduce your input, and then you'll get less pollution the whole way through, or you want to concentrate on having a bigger output. I can see some hearts coming up. That's never happened in the talk for me, so that's nice. So the same can be applied to phosphorus, I guess, or it can be. So we shift on to the next principles, a transition to a circular system. We're all talking about that and we're all aware of that. and then strategies aimed at jointly decreasing nitrogen and phosphorus and other nutrients are a win-win, and that's incredibly impertinent because because nitrogen and phosphorus share so many similarities in terms of fertilizer production, fertilizer use. Management strategies should be developed with consideration to local physico-chemical conditions. We had to say that in the database. You can't start talking about highly technical measures if you don't have a farm that can carry them or use them or afford them. So within any integrated strategy, you have to consider that. Measures have to be cost effective. They have to be relevant to the stakeholders. And all stakeholders should share responsibility. It shouldn't be just dropped on your farmer. Your farmer has a very small control over the cost of food production. It's, you know, the big supermarkets that are driving that. Their power to implement measures is really constrained economically. So it has to be a whole chain effect, and that includes consumers and everyone on the call as well in that. And then there's possible trade-offs, which require priorities to be set. You know, are you bothered about greenhouse gas? Are you bothered about your lakes? You find there's also great points where there's win-wins, where you say, well, actually, if you fix your lakes, then you reduce your greenhouse emissions through methane production. So there's trade-offs to consider, and that has to be really decided by the policymakers, I guess. Okay, so we just get to the database, and then I'll finish up. So the database, it was built with an idea for accessibility of data and information. So it's a huge amount of information, 140 measures. There has to be a great user experience. We want people to engage with it. It has to be easy to use. It has to be updated easily by people that are going to use it. Each database, each measure within the database comes with a summary, and that gives a very quick look at how much impact that measure will have on the nitrogen loss. It's color coded. You can see there on the left, there's a large reduction, medium reduction. It gives an idea of reliability, and that's if you're a policymaker, do you want to only use very robust measures that are very proven? The next level is this research is promising. It hasn't been proven outside a lab scale, or there's unproven. And the idea is that as your technology innovating, people are coming along, they would say, I'm going to submit my measure to the database. And as they get more lab scale evidence, their measure may go from unproven up to promising up to robust. And then the technical requirements, which gives a sort of idea of scale of costs. That's a kind of overview of an opening sheet of the measures database. I'll show you the data. Actually, I'll just show you it right now. And then we can cut through slides. So this is the actual database online. We have all your measures down here. You click on one and work for me. There you go. And you fly into the measure and you have an overview. That's wonderful. I picked the one measure on there that doesn't have lots of information on. Let's go for this one here. It has an overview. It has the measure efficiency, which is a lit review for all the modelers out there. There's lots of information on that, on percentage efficiency, how to implement the measure, benefits. You have drop downs, you have costs. It gives you a rough idea of capital costs, operational costs. You have risks, and then you have references, and then you have the author you can contact directly for more information. And that covers all of your different sectors that we've just shown you there, and will mean that I can skip past this slide, past that slide, past that slide, and finish off to say, you know, this database is a communication triptych. That means to say that there's the database. It's also summarized in an INA chapter. That's a chapter for this big international nitrogen assessment, which will be coming out soon. And it also has a guidance document, which takes your database measures into a support report that tells you how you have to integrate them, how you put them into any catchment so they get all the win-wins. The next steps for this is where we take this database. Well, where do we take it? Do we take it for a focus on recovery, nitrogen recovery technologies? Maybe we bring it into a policy database, a measures for sustainable phosphorus management. Maybe we have a nitrogen solution, nature-based solutions for aquatic systems. We could maybe do a database on that. We pull that all in, and we're going to use those resources in the very last slide here, which is the project that Brian and I are working on, which is Upcycle, which has just recently started. And we'll be using the database infrastructure to try and present the measures for restoration of lakes globally, and with a focus in Chile within this project. So it's a 2-year project. It's Jeff and UNEP again with $2 million. It's bringing together experts in global lake management and sustainable phosphorus practices to deliver ecosystem recovery and inclusive economic growth by reducing phosphorus emissions. If you want any more information on that, send us an email, and that's me. Thank you very much.
Thank you very much, Will.